Alright, so now it's time to reverse some bits. This is the bit manipulation section, and we're going to do the reverse bits problem, which is an easy. So we're going to go here and on LeetCode.com/problem/reverse bits/description. So reverse bits of a given 32 bits unsigned integer. Okay, what do you mean by this? Reverse bits of a given 32 bits unsigned integer. Okay, so over here we have a note that in some languages such as Java, there is no unsigned integer type. In this case, both input and output will be given as a signed integer type. They should not affect your implementation, as the integer's internal binary representation is the same, whether it is assigned or unsigned. In Java, the compiler represents the signed integers using 2's complement notation. You go open this up. Therefore, in example 2 above, the input represents the signed integer -3, and the output represents the signed integer -1, 0, and all this, the biggest number. Now, I mean, not that big, but you got my point. Example 1. Here we have an n, which is all these numbers. All right. And then we have output is this, and then we have this thing as its binary. The explanation, the input binary string, this represents the unsigned integer this, so return this, which its binary representation is that. Okay, example 2, the input must be a binary string of length 32. Follow up, if this function is called many times, how would you optimize it? So basically, this is the the binary thing. So it's reversing the bits. It's a reverse bits of a given 32-bit unsigned integer. Now we have an unsigned integer in C++. In Java, there's no such thing as unsigned integers. So in this case, both input and output will be given as a signed integer type. They should not affect your implementation, as the integer's internal binary representation is the same, whether it is signed or unsigned. Now, in Java, the compiler represents the signed integers using 2's complement notation. Therefore, in example 2 above, the input represents the signed integer -3, and the output represents the signed integer, this one. So if you look at 2's complement here, is the most common method of representing signed, positive, negative, and 0 integers on computers, and more generally fixed point binary values. Now, 2's complement uses the binary digit with the greatest place value as the sign to indicate whether the binary number is positive or negative. When the most significant bit is 1, the number is signed as negative, and when the most significant bit is 0, the number is signed as positive. Unlike the 1's complement scheme, the 2's complement scheme has only one representation for 0. Therefore, the 2's complement scheme has only one representation for 0. Furthermore, arithmetic implementations can be used on signed as well as unsigned integers, and differ only in the integer overflow situations. So basically, telling you the procedure for doing 2's complement. So you kind of like understand this is the unsigned value and signed value, 2's complement, and then basically these are the things here: signed value, 2's complement, unsigned value, and signed value. So you kind of understand this understanding here. This is the complete theory, but what we're going to do is now we're going to try to implement this. So let's try to break up this problem, because right now we have an input which is a 32-bit number. I believe it's like that because it says over here that input must be a binary string of length 32. So this is a 32, I assume, and the output is this, which is this in binary. Explanation: the input binary string this, which is on the top, represents the unsigned integer this one. So return this, which its binary representation is. I don't know, but it's doing it based on something. So do you see any reverse of it? So let me see. If this is this number, okay, the output is something like this. What I believe is that maybe this is going backwards. So it's like 0, 0, and then 1, 1, 1, and then 0, 0, and then 1, right? And then 0, and then triple 4. So you see ones. And then you have these 1, 2, 3, 4, and 5, 6. So So 1, 2, 3, 4, and 5. Yeah, I believe this is the thing. And then in the beginning we have how many zeros? We have 6 zeros. And over here we have 1, 2, 3, 4, 5, 6. Yep. So basically it's a flip. And this is how it represents in decimal. So unsigned integer this, so return this, which is the binary representation is. Okay, now we have this input. And then when we flip it, it's this, right? And that's this number. So input was n is equal to this, which output is this. And that's the decimal notation. Explanation, the input string, binary string is this, right? Represents the unsigned integer this. So return this one, which its binary representation is that. Kind of understand now. So yeah, it's a flip. It's complete flip. So how are we going to go about this? Now you have this reverse bits function. It returns an unsigned int 32. And we have the input as an unsigned int 32 n number. So what I'm going to do is I'm going to say unsigned int, and then we have underscore unsigned int 32 underscore t, and then we have result is equal to 0, and then we have for int I is equal to 0, I is less than 32, then we have plus plus I. Okay, so over here we have the operation here. What we're going to do is we have this unsigned int 32 result, which is 0, and then we have this function. But how are we going to go about this, right? We're going to go about this with a particular scenario. And what I'm saying is that, okay, so we have an unsigned int 32 result. We put it as this. Then we have a for loop that goes from 0 all the way to 32. Basically, it's going to go 32 times. And what I'm going to do is I'm going to put the result. You see the result, which has 0. It's going to have this result, and then we have this left shift operator by, I mean, we're basically using left shift operator, okay? The reason I'm using left shift is because I'm trying to reverse it. So I get the number, left shift it, and I do this, which is result. And inside the result, what I have to do is basically I have to say either result or the bitwise operation with 1. Okay, this bitwise operation will give me whatever the number is. If it's 1, good, right? So either this or the result, and we store it inside result. Like that. Then we have this other operation where we have right shift operator by 1. And then we essentially return the result right here. This is going to flip the entire thing. And I'm going to explain the whole process here. So what's happening here is basically what I mean by this is essentially n is equal to n, and then we have right shift by 1, kind of like this. Okay, control and comma, and now what we have here is accepted. Okay, it reverses the whole thing, which is pretty neat, I guess, because we have this input which has this group of things. And then the output would be this, which is perfect. Same thing goes for this. We have this input, and the output is this. Now I want to explain this whole process because we need to really understand how this is working. Although it's pretty basic and easy. So we have an unsigned int 32 reverse bits, and it accepts an unsigned 32 number. It has a result variable declared, which is assigned to 0. After that, it goes through a for loop that goes from 0 all the way to 32. It basically has this result, and what we're doing with the result is we're left shifting it by 1. Once we do that, once we actually do this, we now go here, and what we do in here is we essentially bitwise AND this. So bitwise and this is actually bitwise OR, this operation right here. Okay, so we're not using the OR operator, but we're using bitwise OR. And then once we have this operation done, so we left shift to basically flip the whole thing, right? We get from the most significant, and we try to bring it back over here, right? So that's why we're trying to put it within the result. And then what we do is with the number, we just right shift it. So we know that we already did this one, and then we break back to this part. And then we do the same exact thing. Again, we get this number and bring it back here. And then we do right shift by 1. So we have 1 left, and then we just keep continuously doing it until we have this entirely thing flipped. This is going to be our result. Okay, I hope you understood this process, because this right shift n by 1 basically means this right shift n by 1 means that we to get the next bit, and exactly that's what we're doing. So rid of the old significant bit to get the we're basically getting rid of the old least significant bit and just continuously doing this until the whole thing is flipped. The result is really good. I'll just have one sort of explanation here on ChatGPT, and then we're good to go. So I'll say explain the following code. Now the code defines a C++ class named solution with a public member function reverse bits. This function takes an unsigned 32 integer, okay, n as input and returns another unsigned 32-bit integer, which is n, with its binary representation reversed. So we have the function takes an unsigned 32-bit integer n as input and returns another unsigned, which is n with its binary representation reversed. Here's how the code works. It initializes an unsigned 32-bit integer result to store the reverse bits. It iterates through each bit of the integer, n, 32 bits in total, starting from the least significant bit. So it basically starts from the most least significant, which is right here, right? What we did over here was we pick up the least significant bit from here, okay? We put in the result, and we do the next operation. Inside the loop, which is, inside of the loop, it shifts the result 1 bit to the left. This effectively moves the existing bits of result 1 position to the left, making space for the next bit to be added. It sets the least significant bit of result by performing a bitwise OR operation between result and the least significant bit of n. So the least significant bit of n, which is basically this one, and the OR operation with the result. This operation extracts the least significant bit of n using a bitwise AND, with 1, and then sets that bit in result using a bitwise OR operation. And then sets that bit in result, so using a bitwise OR operation. And then after that, what we do is it shifts the bits of n one position to the right. So it constantly like changes this flip here. So we keep going right, 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 right? I told you the representation here where it keeps going right until, you know, all these things have been switched, right? Once this effectively moves the next bit of n for the next iteration. After this loop completes, the function returns the reverse result. In essence, this function reverses the binary representation of the input n by iterating through its bits, extracting each bit from n, and setting it in the correct position in the result. So basically, that's exactly how the solution is done. That is tremendous, and you know, an excellent explanation. If you want just one more, go through of this, I would recommend writing the code out by yourself and try to understand it. And if you have a better explanation, you can leave in the comments. Now, you already know that we have this, we got this result, and this basically result has the copy of the number n, but in reverse format, where we put that 0 initially, and then we go 32 times, we get the results, left shift, least significant bit, and you basically add that in the result. So right now, result doesn't contain anything, but it's always gonna get the most least significant bit, and it's gonna either get the result, and then it's also gonna get the number from here, which is the AND operation. So bitwise AND with 1, it's just gonna reverse it, and we're gonna use the OR operation over here, bitwise OR. We're gonna put in the result. After that, we're just gonna keep constantly left shifting until we have the whole. So it's just going to discard the least significant bit until we have the whole number done, and once the number is done, we'll have the result containing the entire flipped number. So yeah, that's pretty much it. Hope you like this explanation, and we'll continue our series in the next video.